Okay, hi everyone. We're going to talk about the traditional and digital film and then occlusal technique. This is what we talked about in lab. So I just wanted to record the lecture so you could re-listen to it or go over it again. You're not going to need these two objectives: explain the use of safe light, discuss maintenance of automatic film processors. You don't need those two objectives for this one. I want you to be familiar with what's inside of a traditional film packet. It's sealed up in this plastic. Sorry, you're going to hear my dog whining a little bit. If it gets too bad, I'll stop the recording. It's sealed up in this plastic pouch, and you can open it, and there's the lead sheet, the black paper to block out the light to keep the film as nice as possible before you purposefully use the X-ray, and then the plastic film that's inside. And you can either have one or two plastic films, and the speeds vary, but most often right before they went to digital, most everybody used the speed F. Okay, he's going to be too noisy. So the film of the traditional film is what's used to record the image, of course. And the film has an active emulsion sort of painted onto the plastic base, and it's mostly a silver halide. It's mostly composed of silver halide crystals. And when the X-ray photon hits the surface of the film emulsion, a latent image is formed, or you can think about it, like I said in lab, you'll see the image later. So it's a latent image. It's an image that's there. You just can't see it yet because you haven't developed it. And so this here again is sort of a very blown up image of the layers. You have a clear protective coating over the emulsion that has the silver alide crystals. And then you have the plastic base. And then on the other side is the same, the emulsion and the protective coating. So in the film processing, it converts that latent image to something you can actually see, a visible image. And then it also preserves the visible image. Okay, hopefully all that crying is over. Sorry about that. Okay, the development takes place over time. So on the top, this image shows the latent image where all of the silver halide crystals that got radiation changed chemically. And so they kind of like tags them as the ones that are going to change once you get into the development process. Then this bottom picture shows the silver deposited where the film was exposed to the X-rays. The film is placed in a chemical known as the developer solution for a specific amount of time and at a specific temperature. The developer distinguishes between the exposed and the unexposed silver alide crystals. The developer initiates a chemical reaction that reduces the exposed silver halide crystals into black metallic silver and creates a dark or a black area on the dental radiograph. The unexposed silver halide crystals remain virtually unaffected by the developer. So they just sit there. They don't do anything during the development process. During fixation, fixation removes the non-developed crystals from the film, produces light areas or the film where the X-rays there was very little exposure from the X-rays, and then it preserves or fixes the developed crystals and hardens the emulsion to protect the film. So the film is placed in a chemical, oh my word, now my daughter's yelling at me. Hold on. Okay, so the film is placed in a chemical known as the fixer solution for a specific amount of time. The fixer solution removes the unexposed silver alide crystals and creates white or clear areas on the dental film. Meanwhile, the black metallic silver is not removed and it remains on the film and gets fixed. The digital imaging, these are the objectives here, explain in general how digital imaging works, compare and contrast direct and indirect, identify the use for various special imaging techniques, identify advantages and disadvantages. So what is it? It's a filmless imaging system. Computerized imaging system converts energy into a visual image. Preferable to use the term image instead of radiograph, but like I said, a lot of people still say X-rays or radiograph. Couple other terms: pixels is the tiny storage dots that compose a digital image. Spatial resolution, the number and size of pixels within an image. More pixels in an image, the greater the spatial resolution, which means it'll be sharper and clearer. And here's an example: 1 pixel or 4 pixels or 12 pixels, or I guess 16 pixels. Can't really distinguish anything, but the more pixels, the sharper and clearer until you have a nice clear image of what you're looking at. 2 types of digital systems: direct system, charged coupling device, CCD. The sensor is in the patient's mouth, and when you expose the radiograph, it instantly shows up on the computer. Indirect system, photostimulable storage phosphor plates, PSP. There's a sensor, so to speak, or this phosphor plate in the mouth, but it's not connected to anything. You have to scan it to get the image off of it. For the charged couple device, the composition is the sensor contains a silicone chip with an electronic circuit embedded on it. The silicone chip is sensitive to X-rays or light. It's visualized as a grid of pixels or wells where electrons are stored after exposure. You can think of that as equivalent to the silver halide crystals on a traditional film that change. So the more radiation, the more electrons or charge is trapped in a pixel. Less radiation, the less charge or electrons in a pixel. The advantages of the direct digital imaging is that the image is instantaneous and there's greater resolution. I actually think there's something behind this picture. I'm going to have to go into the original and see what else is there. Some disadvantages are: cannot use conventional film holders, must use a barrier, cover, or sleeve. You cannot autoclave it. The wire can be captured in the image, so you have to be careful of that. It's rigid and thick, and there's only one, or actually 2 sizes, a pedo and an adult. For the photostimulable storage phosphor plates, it's a 2-step process. It is wireless and the plates are reusable, and they're a little bit more flexible, a little bit more similar to a traditional film. So it's kind of almost like a hybrid. For the indirect digital system, you need some different equipment. You need these reusable phosphor plates. You need these little shields or sheaths to go over each one. You need a laser scanner and a computer and the software. This is a picture of the scanner, and it goes through, scans the image off of it, and then it clears it so you can reuse it. So advantages overall for digital imaging: it saves time. There's no darkroom, no chemicals needed. The image is enhanced. There's lots of different ways you can enhance an image for checking, looking at bone levels differently, looking for lesions, periapical lesions with different sorts of enhancements and colorations, reversing the black and the white areas. So different things you can do to try, and you can lighten or darken the image, try and help you see decay. There's less radiation for digital imaging. The images can be shared readily with others. It has led to improved workflow. The hygienist or assistant don't have to kind of stop and go into a dark room and develop films. There's long-term cost savings, and there's advancement in patient education. Even with all of that, though, lots of studies still say there's no diagnostic difference between various film speeds and digital imaging, and no difference between old systems and new ones, even with the improvement in the resolution. Most studies show no difference between digital and film for evaluation of bone levels. So in general, they could diagnose just as well off of traditional films. The concerns are there is an initial startup cost, can be tens of thousands. Sensor dimension is smaller than the plastic housing, but I do think that that's actually improved over time with the newer sensors. It is smaller than a film, which is nice, but it is thicker than a film. So there's just differences in shapes. Rigid, thick, more difficult to place at times. Some people think that, some people don't. Reduced patient comfort, although some patients think it's more comfortable. So it just sort of varies. Increased risk with handling expensive item. Regular special sensor holders because of thickness. Requires special sensor holders because of the thickness of the cord with the CCD, the charged coupling device. The last one is occlusal technique. So name common uses for occlusal radiographs, describe and demonstrate proper technique for taking occlusal maxillary mandibular radiographs. So important to note that in general, the kind of traditional size of film would be size 4, the large one, but you can take occlusal films with a regular size 2 or digital sensor. It's just laying it horizontally on the occlusal plane and taking one on the maxilla and one on the mandible. Very, very commonly used in children to take occlusal images of children's maxillary and mandibular anterior teeth. It is based on the bisecting technique. It's important for you to know that. And it most often examines anterior areas. Head positions, typically just maxillary occlusal plane is parallel to the floor, and the head is mid-sagittal plane is perpendicular to the floor, but you can tilt the chin back as well with some of these. The common uses: localizing foreign objects in the maxilla or mandible, locate supernumerary, unerupted, or impacted teeth, evaluating extent of disease in the jaw, detecting stone in submandibular gland, for patients who cannot open their mouth, for children too small for periapical films. Mandibular topographic film is generally good for like a lower anterior of someone who can't really open their mouth very wide. You'd place it back on the mandibular teeth with the occlusal plane parallel to the floor. The mandibular cross-section, you'd have the patient tilt their head up because you really want to get underneath the chin. And this is a great one for looking at the submandibular glands to see if there's a salivary stone. And a salivary stone is called a sialolith. And this is what it would look like on a film, or it could even have more little white areas if there's several stones. Maxillary topographic would be your equivalent for the maxilla as was on the mandible, mostly to see anterior teeth, but also to see if there's impacted teeth. You note that there's a lot of foreshortening because, again, this is a bisecting technique, so there's going to be a lot of distortion. Maxillary lateral films are great for seeing impacted teeth, and you can see maybe a little bit more of the teeth from this view, but it's still, there's a ton of foreshortening, lots of distortion there. But you can see in this image, it's really good for seeing the impacted tooth or the impacted canine. And that is it. Sorry about all the noise earlier.